All right, now for something completely different. This is out. I don't know how to say this. We have this lemma. Sometimes it's called an identity. Depends on your source. Okay. We've been talking about modular arithmetic. Now we have a theorem about modular arithmetic. Where do I have the proof of this written down? Here it is. Okay, cool. Let a and b be integers let these be integers, and let d be the greatest common divisor of a and b. So this is the largest integer strictly greater than 1, which divides both a and b evenly. Okay. Then there exists x and y integers such that ax plus by equals d. And in fact, the set ax plus by, where x and y are integers, is precisely equal to the subset generated by, or the set generated by d. And I'm actually going to write this out because this statement does not take place technically in modular arithmetic. So just write this as dx, where x is an integer. So this other fact, I mean, I might mention it again because it follows in a pretty straightforward fashion. But we're not going to. It's not important for our purposes. We're not going to use it. But it's just that like all integers of the form ax plus by, that set is equal to the set of all integers of the form dx. Okay, so let's prove this. And this proof, it's basically from Wikipedia. Okay, so given a and b non-zero integers, why are we specifying non-zero? Because, yeah, the greatest common divisor this doesn't make sense without, the statement doesn't make sense if a and b if either of these are 0. So given a and b, okay, so I guess this could have been part of the problem statement, but whatever. Let S be precisely the set ax plus by, where x and y, again, are in Z. So integer combinations of a and b. Okay. But also such that ax plus by is strictly greater than 0. Okay, so all strictly positive integer combinations of a and b. Okay. S is not empty because either a is in S or minus a is in S. Basically, if a is positive, then you just take x equals 1, y equals 0, and you get a, which is an element of S. And if a is negative, then you multiply, then you take x equals minus 1 and y equals 0, and then you get the element a, which is in S. And it's going to be positive in that case. Because, because if a is negative, then minus a is positive. And you can show that, and minus a is going to be in S. Okay. In that case, because it is positive. Okay, so by the well-ordering principle. It feels weird to use the well-ordering principle in this situation, but I guess it's not. I'm sure if I worked in this space more, then it wouldn't be unusual. But yeah, this seems like straightforward. Like this seems like straightforward enough of a proof that you shouldn't have to use like this sort of machinery here, but it just pops up because basically what we need is S has a minimal element that we will call D prime. And let's say it's just AS plus BT because it is some integer combination of A and B. So let's just say those integers are S and T. So we will prove D prime is actually the greatest common divisor of A and B. Okay. By the way, we needed S to be non-empty because the well-ordering principle only applies to non-empty sets. But yeah, so this minimal element, this is like the smallest possible positive integer combination of A and B. Great. Okay. So, and we're going to prove that this turns out to be the greatest common divisor. So what does it mean? So we need to prove that it's the greatest common divisor. I.e., we need to prove that it is a common divisor. So D prime divides both A and B, and it is the greatest common divisor, meaning that if C divides A and B, then C is less than or equal to D prime. That's what it means to, this is precisely what it means to be the greatest common divisor. It has to be a common divisor, and then any other common divisor is less than or equal to it. That makes it the greatest common divisor. Okay, cool. So, to prove that D prime divides A, we'll note that A is equal to D prime times Q plus R for some integers Q and R in, integers Q and R, where R is at least 0 and less than D prime. Okay, and why is this true? This is true. This is just sort of how like arithmetic. This is basically arithmetic modulo D prime. So so basically, A being so any integer. You can get to any integer basically by like taking some multiple of D prime and then adding a remainder to it, which is strictly less than D prime. This is just how like division with remainders works for integers. Okay, so we know that we can write this. Okay, so then what do we have? We do some math. We have R equals A minus D prime Q. And this is A minus Q. And what is D prime again? We know by definition this is AS plus BT. And then we can sort of rearrange these things. So this is, so multiplying it out, A minus QAS minus QBT. So then this is going to be a times 1 minus qs plus b times minus qt. Okay. And so where does this live? So this is a integer combination of a and b. And we know it's greater than or equal to 0 because r is greater than or equal to 0. So so either it is 0 or it's strictly greater than 0. And if it's strictly greater than 0, then it belongs to S. So this is an element of 0 union S. Because either it's equal to 0, because if it's not 0, then it is a strictly positive integer combination of a and b, which is precisely the set of such numbers is what S is defined as. Okay, so now since r is less than d prime, strictly less than d prime, and d prime is the smallest positive integer in S. So, well, S is defined to only contain positive values. So the smallest element of S R cannot be in S because if R is in if R were in S, then R would be an integer combination of a and b, which is positive and strictly less than d prime, which contradicts the fact that d prime is the smallest element of S. Okay, so that means precisely that R equals 0. Because we said it at the beginning that R was either 0 or an element of S, and it cannot be an element of S, so it has to be 0. So R equals 0. So A equals D prime times Q. So D prime divides A because the divisor is Q. You multiply D prime by Q and you get A. Okay, so D prime divides A. Repeating this argument with B in place of A yields D prime divides B. Right, because literally the fact that, so we wrote A equals D prime Q plus R. We could also write, so you could write B equals D prime S plus T. Oh wait, we're already using S and T. There's not enough letters. But the point is this argument, you repeat the same argument, but for B instead of A, and the same argument works. It's just, it will look identical to this, except like A and B will be sort of like flipped. And you will get that B is D prime times an integer plus some remainder, and that remainder is either an S or it's 0, and it cannot be an S, so it has to be 0, and so so that leaves B as a integer multiple of D prime, which means that D prime divides B. Okay, so now we have D prime divides A and B. Great. So that's part of the way there. Now we need to prove that if C divides A and B, then C is less than or equal to D prime. Basically, we know that D prime is a common divisor of A and B. We need to prove it's the greatest common divisor. Okay, so if C divides A and B, then we can write A equals CU plus B equals CV for some integer integers u and v. So we can write D prime. Remember, D prime equals AS plus BT. And then we replace A and B, so we get CUS plus CVT. And we can multiply out the C, US plus VT. Okay? Okay, so then C, we can take C and multiply it by some integer and get D prime. So this tells us that C divides D. And this tells us that C must be less than or equal to, D prime. So C must be less than or equal to D prime because D prime is strictly greater than 0. Yeah. The fact, so C is an integer that, so if you have an integer that divides a positive integer, that dividing integer either needs to be smaller, it needs to be smaller. Yeah. So there we go. So that tells us that if C is a common divisor of A and B, then it is less than or equal to D prime. So D prime equals D. So D prime is the greatest common divisor of A and B. So that confirms that if A and B are integers, then if A and B are integers, then some integer combination of A and B is equal to the greatest common divisor of A and B. Okay, so now let's go all the way back to what we are trying to prove.